Welcome, everybody. Good morning, good night in Korea. It's a pleasure for me to introduce Sanghyuk. Actually, I met him during my internship in Naver in France. And right now, he actually is a research scientist and tech leader in Naver AI. He works on machine learning and its applications. And if I'm not wrong, correct me. In particular, your research interests focuses on bridging the gap between topics, right? Reliable machine learning tasks, domain generalization, uncertainty estimation, explainability for evaluation, and also learning with limited annotations such as weakly supervised learning and self-supervised learning. You have contributed with several products and code and approaches in Naver AI. You also have published in very important venues. So without further delays, I give you the introduction of Sanghyuk Chun.
Okay, thanks, Andres. Yeah, so I'm Sanghyuk Chun. As introduction by Andres, I'm working in Naver, which is a IT company in Korea and also has a location in France. Naver is Europe. Yeah, so I'm gonna talk today about the my recent works on the cross-modal learning. So let me share my screen first. So you can find this slide at my homepage here. So today I'm going to talk about two things. First one is the probabilistic cross-modal embedding presented in this CVPR. And the other one is a new optimizer named AdamP presented in last iClear. I know we only have about 45 minutes, so maybe I'm going to skip a few slides, so you can follow up the details for my paper or the shared slide. Okay, so I'm gonna first introduce the cross-modal retrieval task very briefly and the many-to-many correspondence problem I'm focusing on. And also I'm going to introduce the probabilistic embedding, the major approach of this task and this method. And also for implementation details, maybe not, not explained detailed in the paper. And also I'm going to talk about some evaluation protocol and experimental results. Okay, so I presume that you are already familiar with this task. So here I'm only focusing on the image to text or text to image retrieval task. So we want to find a given query image, we want to find similar captions or vice versa. We want to find images similar to the given caption. So we want to make matching them in the shared embedding space by using the triplet loss or contrasting loss, which makes the given image text pair be closer together if they are matched or not. Further away if they are not matched. One very big problem of this cross-modal retriever is the many-to-many correspondence. For instance, this is the only one paired ground truth caption in the MS COCO, but actually there are a number of images that is for the, matched to the train is on a track next to a platform. So this is a kind of common concept, and we know that a number of images can be matched with this specific concept. So this one-to-many mapping challenges is happening in image to text and also text to image retriever. So first of all, an image potentially can be matched with a number of different captions, it's like this, because people describe different things for the given image. And also the other thing is that image is very exhaustive information, which means that so we use some image sensor photographic sensor to capture whole pixels in the image, but for the caption, people just generate them by their own concepts. So they are actually biased, and also they are selective concepts, not the not contains whole concepts in the image. So these problems causes the one-to-many mapping challenges in this task. So previously, a number of work tried to solve this problem. For instance, this paper, PVSC paper, polynomous visual semantic embedding, solves the problem by multi-head approach. So they extract K embeddings for given instance and compute the K-square distances to find the best matched concept here. But here we propose a new, different approach by using probabilistic embedding. So this work is joint work with Sanghyuk Chun, Rafael, Yanis, and Dian. So we are all from Naver. So this is a kind of preliminary of this work. So there is a work for probabilistic embedding before. So this paper, iClear paper, proposed probabilistic embedding, which maps the given input to the probabilistic distribution, not the point vector. So for instance, here, you can see that 17 and 47s are mapping to the red and blue dot here. And assume you have some, occluded sample. And, this sample potentially can be matched with either 17 or 47 or 77, 97, whatever. But if you use point embedding, it just maps to the specific point. So it cannot, represent any ambiguity of the given input. But if you use a stochastic embedding or probabilistic embedding, we can use the probabilistic distribution. I mean, if some data is uncertain, then it will be mapped to the very large size of the distribution as shown here. So here, the authors maps to the given input to the two-mode Gaussian. So it matches to these two different instances. Okay, so this is technical details, but I'm gonna just skipping the complicated math here. But what you have to know is for the given two instances, we define matching probability and mismatching probability. So here, M means the matched or not. So probability of the given two pairs are matched here is defined by the Monte Carlo sampling approximation here. So it is actually almost same as the assume you have j equals 5. Then you first sample 5 samples from this yellow Gaussian, and then you sample 5 points from this red Gaussian, and you compute the pairwise distances from these 25 pairwise distances, and take average. So that is the high-level concept of this matching probability using the Monte Carlo sampling. So it requires a sampling process for the computing the matching probability. Yeah, I will introduce it later, more detail. And this probabilistic embedding is applied for the a number of applications. For instance, for face embedding or the pose estimation. So here, the deterministic embedding maps the low quality face to the specific point outside of the clusters, but the probabilistic embedding maps to the large size of Gaussian to capture the potentially matched with a number of different faces. And this view invariant pose embedding is 2D to 3D mapping problem. So for a given 2D pose is potentially matched with number of different 3D poses. So they just mapping the inputs to the Gaussian to solving this multiplicity of the ambiguity of 2D pose here. Okay, so let's back to the cross-modal retrieval again. So I talked about the problem here. A deterministic point embedding, cannot capture these types of one-to-many correspondence. So it is how it works to capture the one-to-many mapping in cross-modal retrieval. So if a concept or a caption has very broad concept or a common concept, it will has a large variance so it can cover different concepts here, different images here. And also, for a given image, it can be matched with a number of different captions. So this image is mapped the intersection of different captions here. So yeah, it is high-level description of how the probabilistic embedding can solve this many-to-many correspondence problem in cross-modal retrieval. But we have to know about some implementation details to make the probabilistic embedding really works in practice. So I'm trying to explain the things as much as possible, but because we have very limited time, maybe I skip some items. Yeah, first, the question is, how can we map the input to a distribution by neural network? So yeah, it is simply done by, we map the input to the Gaussian distribution with covariance matrix is diagonal. It means that we only need two vectors. One represent the mean vector, and the other one represents the variance vector. So for the given these two vectors, we can sample the instances from these two vectors. So it is very similar to the variation autoencoder VAE approach to make some distribution using the neural network. So for the image instance, we use less than 152 backbone, and then we for caption we use the globe vector and the by GRU to extract the vectors. So for the given instances, we extract two vectors. One is mean and one is sigma. One is variance. So after that, we can define a Gaussian distribution. Okay, and next one is the training objective. So we directly optimize the negative log likelihood of the matching probability. So it means that for the given instance pairs, or so this is image and this is caption, let's say, we compute the pairwise matching or unmatching distribution probability. I mean, compute the matching probability of the four given pairs. And actually, this operation is defined by sigmoid and some simple Euclidean distance. But it is actually can be computed by log sum exp or soft plus operation very effectively. So here is the detail of the derivation. I'm going to skip this, but the thing is that you can compute the whole objective function very efficiently and very effectively by using the pre-implemented log sum exp operation. So you can see my code to how it is implemented in practice. Okay, so the third one is sampling. So in the machine learning or the retrieval problem, we employ negative sampling to get very strong retrieval performance, right? So let's see how can we do this in this very noisy data set. So this is how the COCO data set looks like. So for the given image, annotators in Amazon Talker type the description or captions. I mean, that is how this data set is collected. So so it makes these types of problem. So these four images are all from the COCO, and also these four captions are from different images. So in practice, I mean, in terms of the ground truth in MS COCO, okay, so here A is matched to decimal A, B is matched to decimal B, blah blah blah. But in fact, here a group of baseball players at the pitch is it is matched to B. But anyway, a baseball player swinging a bat at a bow is actually matched to the A, B, and C and D, right? So even if the data set says A and large A and small a is only positive in the data set, they are actually can be matched with very different captions. So it makes a big difficulty during the training. So people use very strong negative sampling here, and because they are usually based on the triplet, they using like this. So this is anchor. So assume we have anchor as the caption. So this is the given caption, and this is the right one is only positive, and collecting the negative from the outside of the positive. So there are, and this is very important because if this anchor negative distance is too larger than the anchor positive distance, then there is no update because the loss will be 0. So people just trying to make some collecting very hard negative from the data set. So this one, hardest negative mining strategy, is the most famous one in this cross-modal retrieval scenario, where these types of sum triplet, which does not sample anything, is actually not employed by the others. I mean, these approaches. Yeah, so instead of collecting every negative to compute this loss objective function, people just using the most closest candidate as the negative sample. So it makes this type of problem. So let's say this is query, train is blah blah. The method B is good and liquid one because it directly training the making the positive pair is closer than any other hardest negative sample from the data set. But in practice, they are not maybe good at global ranking because this objective function only looks the most minimum or the most closest one as the negative. So this maybe causes the some ranking problem in terms of the global ranking. So it and it is really happening. So I will show the experimental results later of this slide. Okay. Anyway, so we avoid to use the hardest negative mining here, but we use the collecting everything as the negative pair instead of collecting the hardest one as the only negative. So it is actually very similar strategy to the clip paper, which it will be presented in upcoming ICML. So they first sample n mini batch, and they just computing the n positives and n square minus n negatives to compute the whole objective functions. So we also use the similar strategy here, and it is possible because two-plane loss has non-zero gradient, only if the distance gap between positive and negative is sufficiently large. But our loss function automatically less penalize some positive match pairs with high match probability, as well as the negative match with high mismatch probability. I mean, it is by nature of this loss function. So we can use the whole caption and image pairs efficiently, where the triplet loss cannot utilize the some pairs with very large distances. Okay, so that was detail of how we can train the probabilistic embedding in practice, and this is another one. So assume we have a trained model, trained probabilistic embedding, and our goal is retrieval, right? So how can we compute the distances to retrieve the items? So first one is we can use the matching probability. So matching probability, as I said, it is based on the sampling. So we sample, let's say we sample J samples from each distributions. We have to compute J square pairwise distances here. Or we can just using the mean values as the feature vector, and we can compute the Euclidean distance. a good thing of this Euclidean distance is, of course, we can just, using the cosine distance instead of Euclidean distance to, more efficient retriever. So it's very efficient and very fast, And the last one is using other probabilistic distances. Because we have the variance information as well, we can employ them during the retriever or computing the distances. And very interestingly, our experiments show that the different retrieval strategy will give different retrieval performances, as the matching probability is the best, Barshowstein is next, and Euclidean distance is the worst. But it is still has good performance as well. So you may think the performance gap between these different methods are very small. So maybe you can use this Euclidean distance if you don't have enough, space complexity, or you have to implement very fast or efficient retriever. If your system requires these types of retrieval scenario. Or if you need more accurate retriever performances, then you can use matching probability. So it is a kind of trade-off between the complexity and the performances during the retriever. And another good thing of this probabilistic embedding is you have variance, right? So you can measure the uncertainty, input uncertainty, by using this probabilistic embedding. So more uncertain input will be mapped to the larger Gaussian, and larger means that you will have more larger variances. So here we use the geometric mean and the determinant of the covariance matrix, or the just product everything in the covariance elements to compute the input uncertainty here. Okay, so that was the implementation detail of PMRP, and I'm gonna talk about the evaluation protocol and data sets for cross-modal retriever. So I introduced this problem before, right? So as I said, even if method A is good in terms of human evaluation, because these three images are all matched with this query. A train is on a track next to a platform. The liquid one, the most popular evaluation metric in this field, cannot show proper ranking between these two methods, method A and method B. So we proposed to, we proposed to use precision rather than Decay here. So in terms of the precision, method A will have 100% precision at 3, but method B will have 33 precision score. The problem is, to measure the precision, we have to, secure the whole classes or the positive pairs. But problem is, because MS COCO is collected by the Tuckers, and the only collection procedure is for the given image, annotators just putting the captions, and just these matched captions are treated as the positive. It is impossible to measure the precision in practice. So it is very big difference between from the other retrieval tasks, like the image-to-image retriever. So this cross-modal retrieval task has no class, so it is unable to compute the precision score very accurately, because there are a lot of false negatives in the dataset. So we propose two solutions for evaluation. So first one is we build a new dataset with clean positive information. So we use CUB bird dataset as new cross-modal retriever benchmark. So this dataset contains 200 different bird species or classes. So we just treat the items from the same class as all positive. For instance, this is a query. So this is, in the class caption, class named Downy woodpecker. And this is retrieved items, and these black woodpeckers are all from the Downy woodpecker class. So we treat these Downy woodpeckers images as the positive of this query. It is possible because these whole captions are description of the given bird image. I mean, in terms of the shape of the bird or the color of the bird. So they are actually used for the zero-shot classification, but we changed the benchmark for the cross-modal retrieval. Yeah, so we just solved this problem by using plenty number of positive pairs using the COCO caption. But in practice, we have to evaluate the performances on the MS COCO because it is the most famous and also one of the realistic benchmark for the cross-modal retrieval. So the other one is we made a pseudo positive for existing data set. Because this MS COCO dataset is, has 80 categories in this dataset. I mean, they have multiple object labels because they are originally made for the object detection and segmentation. So each image has a number of different classes here. So for instance, for this image, there are 4 classes or concepts. Human, bat, glove, and bow. Here, there are 4 different classes, and this is ground truth captions of this image. So here we define a plausible image of the given. We define an image is plausible image if the classes of this image is same as the query image. And this is the plausible captions from this plausible image. So as you can see here, this caption is actually very similar to this query image. Like a man is swinging a bat at a ball, right? But in practice, some concepts or some classes are missing. So we also allow some missing concepts. Like so this eta means the distances between these images. So this is 0. It means that 2 images has exactly same concepts. Eta equals 1, zeta equals 1 means that there are 1 missing or additional concepts from the query image, and zeta equals 2 means that 1 concept can be changed because this zeta is measured by Hamming distance here. So here, okay, the ball is missing, and instead of there is a bench here. Yeah, so we make the pseudo positives for MS COCO using these plausible images, and we measure the precision score using these pseudo positives. Okay, so here are some experimental results. So this is performances by different retrieval strategies. I already showed you before. One interesting thing is there is another trade-off here. So if you increase the number of sampling during the inference, larger number of samplings will give you better retrieval performance. But it will cost a lot. For instance, this 12 sampling requires 12 by 12 is 144 times expensive computation than using the Euclidean distance. So it is purely computational resource versus performance trade-off. And also, as I said, these 2 Barshstein, the probabilistic distance, but the closed form without using sampling is slightly better than mean only or Euclidean distance-based retrieval here. And also also this is results from the COCO caption I showed you before. So one interesting thing is this PVSE is utilizing the hard disk triplet, hard disk narrative mining. So when we increase the K, so by increasing K, this is a kind of hyperparameter of this this method. So whenever you increase the K, the recall is improved, but at the same time, precision score is decreased. So it means that maybe the previous method are too much focusing on the recall, but they don't, treat the global ranking or the precision scores. Yeah, also we observe very similar thing in this COCO, MS COCO results. So this green one is PMRP, the proposed probabilistic cross-modal embedding. So we have the best precision score among these previous method, where these methods are getting larger and larger liquid one score. So it is going PBS K equals 1, K equals 2, and this is VSRN, and this is VSRN plus another one, AOQ. So they just showing better liquid one score, but in practice they don't actually showing worse performance in precision score than our proposed method here. So as I said, previous methods are too much focusing on the liquid one, optimizing liquid one score. Of course, there is one big disclaimer, because this VSRN and VSRN plus AOQ utilize very strong backbones. They use visual genome pre-trained faster ICNN as the visual backbones. So it is actually unfair to compare PMRP and this method. But I want to say that even if they have very strong liquid one score, PMRP actually show better precision score. Even if it use, even though it use much worse, weaker backbone than this method. And this is actual uncertain image examples from the COCO caption using PMRP. So here, these red one are only matched images, I mean ground truth images. But as you can see, so here, the retrieval caption is a surfer riding a wave in a blue ocean. It is actually correct, And also this one is two people in the midst of tennis match on a grass court. This is actually, matched. This is wrong actually, because they cannot capture this a boy and two boys here. But I mean, they are quite plausible in practice. And this is the text to image results. Again, there is only one ground truth here. This one is ground truth and this one is ground truth. But here, for instance, this is Big Bang image with caption is a large clock tower is on top of a building. But there is a lot of buildings has big clock on top of the building. Not only Big Bang. So these images are actually matched with this query caption, but the previous or existing liquid one score cannot capture this plausible matching results. So that is why we propose the precision score as the new evaluation metric. So yeah, as we can expect, this liquid one is highly related to the uncertainty. So we show that by increasing uncertainty, the requirement score is decreasing both in image to text and text to image. And also the uncertainty can capture the input ambiguity. For instance, this is the occlusion hole size or the cutout size of the given image. So but when you erase a bigger hole for the given image, the uncertainty is going large, and same as the text. So this is a random token drop from the given text. The text uncertainty is going larger and larger by the number of removing token is increasing. And this is the visualization of the PMRP embedding. So this being less circle is 99% confidence interval for this bird has blah, blah, blah. And because this data set is whole about the bird, this caption is, actually can capture whole captions. I mean, because whole every caption is describing the bird image, right? And as we expected, this 99% interval covers most of the captions in the dataset. Yeah, it is additional visualization. So this PMRP embedding leaves a richer embedding space where the set algebra makes sense. So here, set algebra, we tested two set algebra. First one is mixing. So we tested intersection. So this is the given images. When we mix two images, the embedding is placed between two embeddings, while the embedding is intersect with the previous images. And also, when we doing some occlusion of the given image, this image, the embedding is slightly larger, become larger than the original image as shown in here. And the code is in the GitHub, so you can use my code. And also I'm also make the Docker environment publicly, so you can use my Docker environment for the reproducing my results. Okay, so here is the conclusion of PMRP. So we argue that deterministic embedding is not sufficient. The one-to-many not sufficient to capture one-to-many correspondence. So we propose probabilistic cross-modal embedding, PMRP, to solve this problem. And also we observed that current cross-modal retrieval benchmark have some limitation on its evaluation. So we proposing focusing on precision, not decay, by using a new cross-modal retrieval benchmark or the new evaluation metric, the plausible matching R precision, PMRP. So PMRP shows better precision score, and also it showed the uncertainty estimation by PMRP shows quite interpretable than previous methods. I just noticed that it is almost 38, so there is no time to explaining this AdamP optimizer a lot, but let me try to briefly introduce this one in 5 minutes. Because this AdamP optimizer is used by this PMRP, and I observed that this optimizer is, can achieve quite stable and powerful performances for not every, but many applications in computer vision or other field. So let's briefly introduce this one. So there are 3 synchronous spaces of neural networks, like batch normalization, momentum, stochastic gradient descent, and weight decay. So we observed that, So this batch normalization makes the scale invariance. It means that the scale invariant parameter means that whenever you just apply times the scalar multiplication, the results are not changed because this is normalization, right? And 95% and 91% of LesNet 18 and 50 parameters are scale invariant. And one big problem one big property of this scale invariant parameter is whenever you update the weight using the stochastic or gradient descent, the norm size is increased monotonically. So whenever you just training the, so after enough number of the iteration, you will have a large size of the norm of each parameter. It is, particularly can be problem because the effective learning rate of the scale invariant parameter is actually, proportional to the inverse of the norm size. It means that if you have larger norm size, the effective learning rate is going down and going smaller. So a paper from last ICLR shows that it is actually not that bad because we can, the convergence property of neural network is actually guaranteed for the scale invariant parameters, even if we have efficiently large learning rate here. But we found that it is not true for the momentum optimizers because they only show the results for the slow SGD. But in practice, we use the momentum optimizers, right? Problem of this momentum optimizer is they just make the norm increases much faster than the stochastic gradient descent. So it is the brief overview of the problem setting. So this lead one is gradient method, gradient descent. So it's very slow, but the norm is not that increased much. But this yellow one is momentum, gradient descent plus momentum. So it looks much faster, but after enough iteration, it shows very slow convergence because the size of norm is actually related to the effective learning rate, and it is become problem when you have much higher or much stronger momentum parameter. So here, this yellow one is momentum, and green one, red one is the vanilla gradient without the momentum. You can see that even if it is faster in very early stage, it is even though it is faster at the first stage, it is eventually slower than gradient descent in later stage of the training. So we propose this green one to reduce this problem. So we use some simple projection-based solution. I will skip the details because you don't have to change anything for applying this one, but just changing the optimizer in your code. I mean, it does not change your architecture or the objective function. Yeah. So the last one I want to mention is so weight decay is another secret recipe of the neural net optimization. We use this weight decay without any consideration, but actually this weight decay is another parameter to control the norm increases I mentioned before. And it makes the performances are very sensitive to the weight decay parameter. So here, when you have larger and larger weight decay, the norm increases are much slower, or the not that rapidly increased. So for instance, without weight decay, you will have about 4 times larger norm. So norm 0 equals 1. And norm 1 equals the norm at the after first apple, and norm last is after enough number of iterations. So it goes to the about 4.3 times larger than previous, and score is actually proportional to this norm size. So by using proper weight decay parameter tuning, you will have much larger performance than no weight decay scenario. But good thing of our method is it is less sensitive to the weight decay because our method is naturally control these norm increases by its our method. So our method is less sensitive to the in terms of the score. This score is less sensitive to the weight decay choice, and we believe it is much drastically effect to the these types of AdamP optimizer, which utilize the second order momentum for the faster training. So you can see it has much larger norm increases than the SGD solutions. So we tested a lot of different tasks and data sets. Of course, we show that ours are much better than previous ones. And one good thing is that we observed that ImageNet classification accuracies actually can be, I mean, AdamP variants are known to that showing much worse performance than SGD in ImageNet. But we found that using AdamP, it shows much better than SGD in some scenarios. And also we tested image retrieval, and it shows the consistent performance increases from the non-projection solutions. And it is exactly same thing I observed in the probabilistic cross-modal retriever. And it works for the other minimax optimization and non-image classification. And you can use this optimizer by just using pbinstall and just change your optimizer from the AdamP or SGD to AdamP or SGDP. So they have exactly same interface as the torch optimizers. Yeah, so this is a kind of conclusion, but let me skip this because I think it is running already out of time. Yeah, so this is the end of my talk. Yeah, thanks for your listening.
Thank you very much. Congrats for your work.
Thank you for inviting me today.
You're welcome, always. Thank you.
Thank you.